In this video, I will show you how to use uniTank for tank calibration analysis. This video starts immediately after you have finished doing automatic classification. Unlike in tank analysis, where we typically use a man weight as the reference, traditionally for strapping, we use the gauge pole, strike, or datum point as the reference. I locate the gauge pole and place a point in the middle of it using the point tool. I then select the Rotate with Point tool to rotate the gauge pole to the north. Remember, whenever you do global transformations like this, make sure that your transform type is set to all so that you don't mess up your registration and so that all the definitions track along with your point cloud. With this new reference, we need to make sure that the bottom shell weld closest to it is set to 0. This is a very important step for capacity calculations, and you will get an error from uniTank if it's not set properly. Because most measurements we get from the field, such as course heights, overflow heights, max fill heights, and floating roof heights, are physical elevations and not liquid level. So if you're using any of these physical measurements from the field, you will need to make sure that they are referenced properly. Typically, these physical elevations are measured from the tank bottom. On the other hand, liquid levels are measured from the strike. So if you are given a max fill height, make sure you know whether it's a physical elevation, such as an overflow measured on the shell, or a liquid level, such as a max fill height from a previous strapping chart. If you have a max fill height that is not based on product overflow, you can set it now. I use the GoTo function to position my view center at the max fill height. This assumes my tank bottom was set correctly at 0, because I'm placing the max fill height exactly at the elevation I was given. You can either use the point tool to place a point at this height, or you can just add the max fill point with no points drawn, and uniTank will automatically use the view center elevation. The max fill point is optional and does not need to be set if you don't have one. You can only have one max fill point. Adding another max fill point will override the previous max fill point. If you have overflow vents in the tank shell, you can go around and add those. I find it's easiest to go around the perimeter of the shell in cylindrical mode. Like adding the max fill point, I can either place a point at the height I want, like in this case. Or I can place my view center at the overflow point with no points drawn, and uniTank will automatically use the view center elevation. Overflow points are optional and do not need to be set if you don't have any. You can have multiple overflow points. uniTank will select the lowest overflow point as the controlling height. Next, I am going to set the strike point. Usually this point is at the bottom of the gauge pole. If there's no gauge pole, then you need to locate the gauging hatch and set the strike point directly below it. I use the point tool to identify the location of the strike point close to the tank bottom. Then I use the Find Plane tool to find the exact elevation of the strike point. This point is very important because it is the 0 point of the strapping chart and the reference point for all the liquid levels as discussed earlier. I have the option of adding the gauge height directly above the strike point. This height is typically measured in field. Here I am showing all the others points, which are the remaining points that do not belong to floor, shell, roof, beams, columns, or floating roof. I am going to run the Auto Detect Appurtenance button to automatically detect all the deadwood. I usually select a range between 0 and 6 feet because this is typically where all the appurtenances are located. If you have a floating roof, you may want to lower the upper range of the detection to avoid the floating roof hangers. Once the detection is done, we can examine the results and modify them as needed. As you see in this case, the auto detection has picked up a lot of the floating roof seal hangers. Using the rectangle, polygon, or circle tools, I can draw a shape around the erroneous appurtenances and delete them. I can either use the Delete Selected tool in the Advanced menu, or I can simply use Shift-Delete. I use the Auto Detect columns to find all the pipe columns. In this tank, there's only a gauge pole. This will not work for structural columns, but I will show you how to handle those at the end of this video. Now, I will delineate the pipes that were missed. First, I measure the diameter of the pipe and note it. Then, I use the line tool to trace the pipe's center line. I toggle between top and side views as I move the view center along the pipe. Finally, I use the Auto Detect Sump tool to find the sump. I only need to draw a circle around the sump, and uniTank will figure out its diameter and depth. uniTank uses the lowest point of the sump it sees, so you may need to make the sump deeper if your scans did not reach the bottom of the sump. To do this, just edit the deadwood and modify the length of the object. uniTank will automatically update the volume of the deadwood when you edit its dimensions. If your tank has a floating roof like this one, you can add it using the floating roof Deadwood tool. I need to know the floating roof weight and the product density in order to calculate the displacement volume and submersion depth. You can set the floating roof height by shift dragging the image in the dialog. Floating roofs are never flat, so you just need to pick a reference point to set the roof height. Typically, we like to use the perimeter. Alternatively, you can pick the lowest point of the deck. Either way, we are setting the first contact point of the floating roof, which will determine our lower critical zone. Finally, we need to calculate the submersion depth to determine the upper critical zone. The volume of the floating roof is solely determined by its weight and the product density, so the submersion depth does not have any effect on the total volume of the tank. We have 4 different options here to determine the submersion depth. First, we have the flat pan, which is used for steel or aluminum pans. The submersion depth is based on the diameter of the floating roof. Second, we have the pipe pontoon, which is used for aluminum floaters with pipe pontoons. The submersion depth is based on the total length and diameter of the pontoons. Typically, these types of floaters are lighter, and usually they are designed to submerge halfway up the pipe pontoon, about 5 inches for a 10-inch pontoon. By design, the pipe pontoons should not be fully submerged, so you will get an error if the overall volume of the pipes is less than the displaced volume of the floating roof. Lastly, we have the wedge pontoons, which is used for external floaters. Referring to the diagram below, you can enter the dimensions of the pontoons and adjust them to match the point cloud. In this case, the floating roof slopes upwards all the way to the center, so the pontoon width runs the length of the radius. Also, by design, the deck of the floating roof must contact the product, so you will get an error if the volume of the pontoon is more than the displaced volume of the floating roof. This means either the dimensions of your pontoons is incorrect or your floating roof weight is too light. Usually, floating roofs are scanned in high leg or maintenance position. Typically, the floating roof volume is deducted from the low leg or operational position. In order to get the low leg or operational position, you need to know the high leg to low leg offset. This needs to be measured in the field. Now we are ready to go compute the strapping table. First, I need to enter some tank properties. For capacity analysis, shell course heights and thicknesses are required. You can enter a single course height or multiple course heights separated by semicolons. uniTank will repeat the last course height and thickness for any remaining courses that are missing. If you have a top angle, you should include that height in your last course height. For capacity analysis, you will need to know the ambient temperature of when the scans were taken. This allows uniTank to calculate the temperature correction factor. I can create 3 different types of reports. The capacity report is the long form containing all the calculations. The image table is the short form containing just the strapping chart. And finally, the image table fractional is the fractional strapping table in 1/8 of an inch or 1 millimeter increments. Once the reports are generated, I like to mark the floating roof critical zones and the max fill area. This is another tank with a heating coil where the auto detection worked almost perfectly. The only thing that I need to do is remove a bit of the end of one of these lines where the auto detect added a little bit of extra piping. At this point, I want to draw your attention to the colors of the Deadwood. To make it simple to recognize, orange Deadwood are items that add volume on the outside of the tank, such as manways and sumps. Blue Deadwood are items that subtract volume inside of the tank, such as columns, pipes, and nozzles. Outside Deadwood is created as solid items because their entire volume contributes to the overall volume. Inside Deadwood is created as hollow items because only the pipe thickness usually reduces the overall volume. The typical exceptions are heating coils, drain pipes, and structural columns. These items are usually closed, and therefore their entire volume reduces overall volume. To make a Deadwood solid, simply change its thickness to 0. I will now show you how to create structural columns. For structural columns, I use the Extrusion Deadwood tool. This tool can be used for any object that is not a pipe. The way this tool works is that you define the cross-section of an object and you extrude it or give it a length to create a 3D volume. So for the columns, I isolate a cross-section of the column and trace it. I then create the extrusion by specifying the direction I want to extrude it. So if I select back of face, the object will be extruded towards me. If I select front of face, the object will be extruded away from me. The second ring of columns has a different shape. First, I delineate one of the columns. If you need to, you can use the manual transform tools to move the Deadwood much like a point cloud. Just select Definition as the type and Deadwood item as the layer. Then using Ctrl-Shift-Drag, you can move or rotate the Deadwood. I modify the height so that it fits the column. Then, I use the point tool to define the additional column locations and select Copy by Name. I want to set all the columns to the same elevation, so I select the same Z as original. Remember that for capacity analysis purposes, the actual orientation or rotation of the Deadwood doesn't matter.